Hello everyone, in this video we're going to learn how to generate and how to analyze time series in Python. We're going to learn how to generate a white noise sequence and autoregressive processes and how to analyze these processes. For example, what you can see over here is an estimated autocorrelation function of an autoregressive process of the order 1. Then, what you can see over here is the actual autoregressive process of the order 1. So in this video, I'm going to teach you how to generate such a process and how to plot or compute autocorrelation, partial autocorrelation, and QQ plots of the AR processes. As always, I have created a post that accompanies this video, and this post can be found on my webpage. I will place the link in the description below so you can read this webpage if you don't have time to watch this video. Okay, so the first step is to install the statsmodels Python library. So how to install a statsmodels Python library? This is super easy, right? You open a command line and you type pipe install statsmodels. Okay? In my case, you will see that I already have the statsmodels on my computer, so I got all these warnings and all these notifications. However, in your case, since you most likely will not have the statsmodels library, you will get the nice screen and you will see the progress, installation progress. Okay, so this is the first step. So once you have installed the statsmodels library, you can reproduce the codes that are given over here. I have also posted the codes on my GitHub page. A link is given in the description below. Okay, so I'm using the Spider Python environment. Why I use this environment? Well, that's a good question. And the answer is this environment reminds me of MATLAB. It's very used to run and to debug the Python codes in this environment. For example, I can just select the code lines that I want to execute and I can just run them. Okay, and you can see the results over here, right? Let me run this part also just to illustrate. Here are the results, right? It's very convenient. This environment is very convenient, and I strongly suggest you that you install it. Okay, so let us jump on the code. So these 4 lines of code are basically just standard imports, right? We are importing here pandas, we are importing the numpy for manipulating arrays or vectors. We are importing Python plot libraries, right? And finally over here we are importing the statsmodels library. Now, this line of code is basically used to set the random seed of the random number generator, right? So what is the purpose of this code line? The purpose is to make sure that the codes that you will see over here are reproducible. Okay? So, by setting up the random seed, I'm telling to Python, in every execution of the code, generate random numbers using the same principle. So, if I generate over here a random time series, right? I'm going to explain in detail how I do that, but however, just for the time being, just focus on this part, right? And if I kind of plot my or print my time series, I can memorize these 2 numbers, okay? Now, if I erase, so let's remember these 2 numbers. The first one is 1.62 and the other one is 0.611, okay? Now, if I erase my workspace, this is how you do that, right? And if I run the code again until this line, And if I print the numbers, you will see that the numbers are the same. They're random, however, they're reproducible. So you can reproduce this on your computer easily. Basically, in other projects, you don't need this line of code. You can just simply comment it. Okay, so let us start with white noise. But before we start, we need to clarify one thing. What is a white noise? We need to explain what is a white noise. Well, a white noise sequence is a sequence consisting of uncorrelated samples. Or you can even say that a white noise is a sequence of numbers that are independent. Watch out, independence is a stronger notion than the notion of being uncorrelated. In fact, it follows that if a sequence is independent, then it is uncorrelated. However, if a sequence is uncorrelated, that does not mean that the sequence in the general case is independent, except if the sampling distribution is Gaussian. Okay, so we set the length of the time sequence. We are going to use 5,000 samples. And then with this line of code, we are going to generate our sequence. So this is our time series. Okay, we can see it over here. Let's plot it. So how to plot in Python? It's super easy. You're just basically just specifying the figure size, and you're similarly to MATLAB saying plot, right? So let us execute this line of code. Notice here that I'm always saving the graphs. It's always a good practice to save the graphs that you're plotting. So here is our white noise sequence, right? Now, the next step is to convert this sequence into pandas time series object. Let's do that. Okay, let's see what do we get. Great. So this is our time series in pandas. You actually do not need to perform this step in this particular tutorial. However, in other tutorials, I strongly advise you to convert your time series to pandas objects. Okay, so the first step in analyzing time series is to generate or to estimate an autocorrelation function. In my future videos, I'm going to give you more theoretical backgrounds on statistics, on autocorrelation, partial autocorrelation, and other functions that are kind of describing mathematically time series processes. However, in this video, since this is just an introductory video, I'm going to skip these theoretical explanations and I'm just going to focus on plots and on hands-on explanations. So remember, autocorrelation plot is a very important plot that can discover many properties of your time series. For example, it can tell you if a series or the samples of the series are correlated or uncorrelated. Furthermore, it can be useful to kind of infer some statistical properties of your time series, such as stationarity of the time series, etc. Let us just, for the time being, learn how to generate these plots. Okay, so to generate these plots, I'm using statsmodels, and I'm using a particular function. So this function, its explanation actually is given over here. So you can go over this tutorial and this explanation to learn how this function works and what are the parameters that you need to provide. Okay, here is the link. I have augmented my codes with links to all the functions that I'm using in this video, such that you can read them later on. Okay, so this line of code is used to generate an autocorrelation function. Why I just don't simply write down one line of code? Well, I was struggling with this, basically with this problem, since I wanted to save my plot into a file, and furthermore I wanted to adjust the basically sizes of the figures. However, I wanted to keep it locally, such that once I set the properties of Python matplotlib function, I wanted to keep it only in this code snippet, right? And I don't want these properties to affect other functions in my code. So somehow I learned how to localize my code. And you can do this with this context, RC context, basically manager. You can find more about it basically in these links that are provided over here. However, you can basically localize your plotting properties with this 3 or 4 lines of code. So let us generate the autocorrelation function. Here is my autocorrelation function. So what can we see from this plot? What is important to observe? Here on the x-axis we have lags, and on the y-axis we have the values of the autocorrelation function. Now, what can be observed? For the lag 0, the autocorrelation is equal to 1. This means that the sample is perfectly autocorrelated with the sample for the lag at 0. So the sample is perfectly autocorrelated with itself. However, we can observe that for the lags 1, 2, 3, 4, 5 until the 40th lag, the values of the autocorrelation function are small, almost 0. So this means that most likely the samples are uncorrelated, and that most likely the samples correspond to a white noise sequence. Now, the statsmodels library gives you even the confidence intervals, right? The shaded region over here represents the confidence intervals. If 95% of these estimates, these small dots over here, fall within this shaded region, then you can say that most likely this sequence corresponds to a white noise sequence. Or moreover, you can say that the samples are basically independent and identically distributed. That's the power of autocorrelation plot. If you had, for example, 10 of these samples that are outside of the shaded region, then you cannot claim that your sequence, or actually the time series, corresponds to the white noise. Or you cannot claim that the samples are independent and identically distributed. If you want to obtain the values of the autocorrelation function, you can do it easily. And in addition, if you want to find the values of the confidence intervals, you can do it with the same line of code. So by executing this line of code, I'm going to obtain the values of the autocorrelation function, okay, and the confidence intervals. You can use these values if you want to do some further analysis, or if you want to use the values to obtain another plot. Besides the autocorrelation function, we are also using the partial autocorrelation function to investigate the properties of time series. And this line of code is basically generating a partial autocorrelation function, or better to say, an estimate of the partial autocorrelation function. Similarly, I am basically using the RC context manager to localize the plotting properties, right? And with this line of code, I'm going to basically generate a partial autocorrelation plot. So if I execute these lines of codes, I obtain a figure that looks like this. Similarly to autocorrelation plot, I see here a very dominant component at lag 1, that's expected, and I see other components that are close to 0 for other lags. This is expected. Basically, the partial autocorrelation function is very useful for estimating the order of the autoregressive time series, and I'm going to explain this in the sequel. Okay, another plot that we usually generate when we are doing preliminary analysis of time series is the QQ plot, right? So the QQ plot is used to compare two distributions, and let us plot it. So here is the QQ plot. So what are we seeing over here? Basically, we are seeing theoretical quantiles and the sample quantiles, right? And the 45 degrees line is basically a measure how far is my distribution, or the distribution of the samples of the time series from the normal distribution. That is, in this case, I'm comparing my time series samples, their distribution, their empirical distribution with theoretical normal distribution. And I can see over here that basically these samples are very close to 45%, or actually 45 degrees line, basically, which is basically convincing me that the samples of the generated time series are generated from a distribution that's maybe almost equal to the normal distribution. We know in our case that that's true, that these statements are true. However, we need to verify it, okay? Besides the autocorrelation function, we are also using the partial autocorrelation function to investigate the statistical properties of our time series. And in the sequel, we explain how to generate the partial autocorrelation function. So similarly to autocorrelation function, I'm going to use the context manager to generate or to plot the values of the partial autocorrelation function. So the codes are equivalent. The only difference is basically that I'm using this function, PACF, plot PACF, okay? So I'm going to execute these lines of code, and here's what I get. Here's my partial autocorrelation function. I see a very similar behavior to the behavior of the autocorrelation function, right? I see dominant component and all other values for different lags are equal to 0, right? So in the sequel, I will explain you that partial autocorrelation function plot is very useful for investigating and for estimating the order of the autoregressive processes. Okay, so the next plot that we usually generate when analyzing time series, or when we perform a preliminary analysis of time series, is the QQ plot, basically. The QQ plot is used to compare two distributions. In our case, we are comparing the distribution of the samples of the generated time sequence with the normal distribution. We want to see how far is the empirical distribution of samples, how far away is it from the normal distribution, right? So again, I'm using a similar principle to generate the QQ plots. The only difference is that I'm basically using this function over here. So here's our QQ plots. This line, this 45 degrees angle line, the red line, is the ideal case, okay? If these dots are lying on this line, then we can say that the samples of our time series are generated from standard normal distribution. And we can see that this is actually the case, right? Most of these samples are very close to the 45 degrees line, right? Except these samples over here. And we can say, well, okay, it looks like our sequence is definitely a white noise, right? It looks like a white noise. First of all, the autocorrelation is very similar to the autocorrelation of the white noise sequence, and the QQ plot is basically confirming that the samples are distributed according to the normal distribution. Next, we explained how to generate and how to analyze autoregressive processes. So in its basic form, an autoregressive process can be represented by the following equation. xk is a sample at a discrete time instant k, and epsilon k is a sample of a white noise sequence. This part over here corresponds to autoregression. So what we can see over here, that the sample at the time instant k is a weighted sum of the sample at the time instant. Substitute here I is equal to 1 and you will obtain xk minus 1, and substitute here number p and you will obtain xk minus p. So the sample at the time instant k is equal to the weighted average of the samples starting from the time instant k minus 1 until the time instant k minus p in the past. Okay, and plus over here you have a measurement noise. P number is the order of the autoregressive process. That's the model order. Usually in system identification literature, P is also called the past window. So this is the order of the process or the past window. And usually autoregressive processes are represented by AR, and in parentheses you put the order pi. So in the sequel, we are going to play with AR1 processes. These processes correspond to this equation. This is how the samples are being generated. Okay, so let us erase our screen. Good. And let us explain how to generate the AR1 time series. Again, we specify the number of time samples, we specify the coefficient. The first coefficient, W1, will be equal to 0.8. Here you should be very careful, because if you specify the first coefficient to be, let's say, to 1, you're not going to obtain the AR1 process. You're going to obtain a random walk. If AR is larger than 1, you're going to obtain an unstable process, although even the random walk process is unstable. Okay, so next we generate the process, right? I'm using a simple for loop to iterate through the equation, to autoregression equation, and in every sample add a random white noise. So let us plot and see what we got. Here is our AR1. It looks very similar to the white noise sequence. It's very difficult to say, is this a white sequence or not? However, if we plot the autocorrelation function, we will see something. This is autocorrelation function. We can see significant autocorrelation between the samples, right? Because the samples are autocorrelated. basically it can be shown by back substitution that samples are indeed correlated, right? Now, I use the same principle that I explained previously to generate autocorrelation plots, right? You can use my code, you can modify it, you can compress it, you can make one function that will plot everything, right? However, for clarity and for simplicity, I keep it like it is, right? So we can clearly distinguish that the generated process here has some autocorrelation structure, right? And it's definitely not a white noise. It's definitely not a white noise. And let us now see the partial autocorrelation function. So if you plot the partial autocorrelation function, we will obtain something like this. So what can we see over here? We can see a value for the lag 1. Value for the lag 1. This implies that the model order is equal to 1, and that corresponds to reality, since our process is generated from or basically is an AR1 process. And you can see how clearly partial autocorrelation function can tell you that the model order estimate, a good model order estimate, is 1. So the p value from the data is 1. Okay, you can see the usefulness of the partial autocorrelation function. Now, let us generate the QQ plot and let's see what happens. So what do we see over here? We can see that we have samples that start to deviate, okay, from the theoretical normal distribution. So our samples most likely are not distributed according to, or they're not sampled from the standard normal distribution. And you can clearly see that these three plots, the autocorrelation plot, the partial autocorrelation plot, and the QQ plot, can tell you a lot about the statistical properties and the nature of your time series. Okay, so this was just an introductory lecture on time series analysis. In my next lecture, I'm going to explain you how to estimate time series, how to do forecasting with time series, and how to basically do even estimation and forecasting of real-world data, for example, of stocks. Thank you very much for your attention and have a nice day.